Okay, so now what we've done is we talked about a slightly more complicated example for how an alkene can react with a hydrogen halide. So again, the first example was this very simple example of an ethene reacting with a hydrogen bromide. And we said that we could potentially have that red hydrogen either attaching to 2 or 1. But because we get the exact same molecule, we really don't worry about the second possibility because it's just kind of repetitive. The fact that we've labeled this as 1 and 2 is one thing, but in reality, there's no real way to tell the difference between 1 and 2. And so effectively, there is no difference between these two molecules. So because of that, since we can't really tell the difference between 1 and 2, we would say then that these are the same molecules just because we can rotate it and they are exactly the same. So because of that, we don't really worry about this second molecule. So for the first example, we only had one potential outcome. And for the second example, we had a little bit more complicated results. Okay, so what I'm going to do is I'm going to start putting labels on these molecules. So let's just say this starting material, or this alkene right here, let's just call this guy starting material A. And this material, this final product over here, will give this guy a letter as well. So this is the possibility B, and this is possibility C. And again, these B and C molecules, these are the final products. But we can also talk about the intermediates. So these, again, carbons with a positive charge, they don't hang around for long. They're consumed to give B and C, but they do exist for a very short amount of time. So we're going to call these guys D. So this is D, and let's call this intermediate E, because these are two different intermediates, so they deserve separate names. Okay, so what we're going to do is, before we can talk about the next part, I have to give a little bit of background about positively charged carbons. So positively charged carbons, they have a specific name. So these guys are called cations, but not just cations. Let's be more specific. These are called carbocations. So the carbo indicates the carbon, and the cation is obviously cationic or positively charged. So carbocations have certain features, and one of the features that we're going to talk about over and over and over again, probably to the point that you probably get a little sick of it, is carbocation stability. So carbocation stability. So carbocation stability, we can talk about how stability can be affected by the overall structure of the carbon that holds the positive charge. So let me give you a couple of examples about different carbocations and different structures for carbocations. Okay, so what you see this is a series of 4 different carbocations. And the way I've drawn them, what you can see is as you go from left to right, you're changing the number of hydrogens that are attached to this center carbon that holds the positive charge. So the center carbon for all of these guys are going to be, here's the center carbon right there, and here's the center carbon here. And all these center carbons, I'm going to give them an orange color. And so if you think about what's attached to that orange carbon, you have another carbon here, here, and here. So this carbocation to the far left with 3 carbons attached, this guy gets a name. And this guy is called a tertiary carbocation. So this little 3, with a degree with an underscore symbol, this is the area, so tertiary carbocation. And it's called tertiary because it has 1, 2, 3 non-hydrogen units attached. So you could think of them as, normally when we say tertiary carbocation, it's referring to a carbon that's positively charged that has 3 other carbons attached, but that's a little vague sometimes. So maybe another way of thinking about it would be 3 non-hydrogen units that are attached. So then if we go over one other molecule, this molecule has 1, 2 carbons and then a hydrogen. So in this case, we would say this carbon has 2 non-hydrogen attachments, and so this is going to be a secondary. And this would have now 1 carbon or 1 non-hydrogen. So we have two hydrogens, so this would not be a secondary because we're not counting the number of hydrogens. We're actually counting the lack of hydrogen. So here we have one non-hydrogen unit, so this would be a primary. And this guy right here, it doesn't have any, so you could name this a couple of different ways, maybe the zero area, I don't know, but the traditional name is, we call this guy just a methyl carbocation. So this would be a methyl carbocation, primary carbocation, secondary carbocation, and tertiary carbocation. So with this series, what you can say then is you can relate these methyls, primaries, secondaries, and tertiaries to stability. So what you can say then is, if you actually were able to do some kind of an experiment in a real laboratory session, and these had to be done at some point, you could say that you could categorize these molecules by stability. And what you would find is that the methyl carbocation is the least stable, and this tertiary carbocation is the most stable of all of these carbocations. So primaries are more stable than methyls, secondaries are more stable than methyls, secondaries are more stable than primaries, and tertiaries are way more stable than methyls. So overall, this is the general trend, is that as you increase the number of substituents that are non-hydrogen, or maybe another way to think about it is as you decrease the hydrogen direct substituents that are directly attached to the orange, then you increase the stability. Okay, so this is another point that really confuses students right off the bat, is that sometimes people will count the number of hydrogens that are not attached to this carbon that holds the positive, but what you really want to go for are direct attachments, what's directly attached to the carbon with the positive charge, or these orange carbons. So again, you want to count the direct attachments and not adjacent attachments. So now what we could do is, now that we've set down this carbocation stability trend, we can try to apply this new knowledge to the mechanism that we were just talking about. So now if we look through the mechanism and try to find the two carbocations that we have, D and E are both carbocations. So we can try to, categorize D and E as a carbocation, obviously, but then we can try to talk about, well, what kind of carbocation do we have? Do we have a methyl, primary, secondary, or tertiary? So now, if you think about this carbon with a positive charge, try to categorize it, and then also try to categorize this E carbocation. So go ahead and pause the video and try to categorize, and then unpause. So one thing that a common mistake is for this intermediate D. Sometimes students will say this carbon, or let's go ahead and give it a color, this orange carbon would be a tertiary. Sometimes they would say tertiary because the student might be counting this carbon, and then this carbon, and then this carbon over here as well. This is a mistake because these three carbons are not all directly attached to this orange. So this orange only has one directly attached carbon, and it's going to be this carbon right here. So this carbon D, if we tried to categorize it, this would end up being what's called our primary carbocation. So this is a primary carbocation. And if we wanted to, we could draw out the implicit hydrogens on this first orange carbon. So if we drew them out, we have one hydrogen here, and then the positive charge because there's no fourth bond. And then if we compare and contrast below, it looks more obvious now for this orange carbon, 1, 2 hydrogens, this orange carbon, 1, 2 hydrogens. But again, we're not counting the hydrogens, we're counting the direct non-hydrogen substituents. So again, if this D is primary, this E would be tertiary because this E carbon with the orange carbon in the center, it would have 1, 2, 3 directly bound non-hydrogen units, or carbon units. So this guy would have a tertiary designation. So between the two, you could then say, okay, which one is more stable? And then the answer would then be, okay, molecule E. Molecule E is more stable because of this inherent stability of the carbocation. And that's going to have broad implications later on in terms of final composition of products. But more on that in the next lecture.